art thou? Finally, finally my refuge. Back to my home, the rocky, beautiful shores. Oh, my home, I'm so happy it's been so long. I've been fighting more battles than I care to remember. The doom, the gloom. First I had to defeat the Cyclops, the one-eyed beast. A fiend so foul that it scares men to death when its gaze falls upon them. But I wasn't scared. I chopped off his head and poked him in the eye. Wah! Then I traveled, trying to get home, to fall upon the lotus eaters. The food they eat makes you forget where you are, where you're going, what you want. But I was so unpleasant, I ate so much of their food, they said, "Stop eating, you pig! Back on your boat to where you came from." I don't know, I guess I wore out my welcome. And then finally, there was Scylla, the six-headed monster that plucked men from my ship. But I was far too fierce for this foul beast. Chop, 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 chop. 6 fell swoops, and each of its heads fell into the whirlpool. Charybdis, another monster. It was men who were doomed in that whirlpool of death. But once the heads of Scylla were falling in, I made a break for it. I rowed my boat. These powerful, massive arms pulled out of the current, and alas, I made it home, free. None of my men survived. But the important thing is that I survived. That's it. So now, I'm going to go have a seat and have a tankard of beverage I have long been awaiting. Well, they did tell me I have to teach psychology. A fate perhaps far worse than being swallowed into Charybdis. But for now, I will do it. Thank you, musicians, for the wonderful show. So, guys, hello. Nothing like a little bit of good Odyssey to make you want to read the Greek stuff. All right, anyway, I'm a king, by the way. Look at that. I'm a king. I'm a king of, I don't know really what I'm a king of, but I'm a king of something. All right, anyway, you guys, so we're going to talk about localization of function in the brain, and then later on now, I'm going to, what am I going to do? I don't know, I forgot. Maybe I had some more of that lotus eater food. No, and then what we're going to do is we're going to talk about a famous study called the Sperry SplitBrain study. The Sperry SplitBrain study. Remember that. Okay? Split brain, no, seems horrible. Anyway, so I said I was going to link the video there in the last one, but I never talked about localization of function, so I'm going to link it now. It's important that you guys watch, especially this first video. Watch the second one, it's good. It's not as important as the first one. The first one, the Bozeman video, he makes a very, very good, just a very good, simplistic, straightforward description and explanation of the different parts of the brain. So watch that, it is crucial. And, you know, I would go over this in class with, you know, little brains. I have brains that you can mess around with, brains. I pulled them out of dead people. No, they're mushy brains. But anyway, mushy brains, sponge is what I mean. Yeah, we can't, obviously. So look at that video, watch that video, it's good. The second one, watch because it's interesting. But anyway, so, and I'm gonna link another thing I'll show you later. Okay, now, here's kind of and I'll put that brain over there. Up that brain goes. So here's kind of a thing with the brain. I'm not going to talk about it too much right now because it's in that other video that I'm going to link and it talks about it pretty well. But here's a sort of side of the brain. There's a cerebral hemisphere. That's up here. The whole thing really. Thalamus, hypothalamus, pituitary, pons, medulla. Yep, the cerebellum is the place for balance. He talks about all of these things. So, like I said, I'm not going to talk too much about this right now, but I'm going to get into the other stuff. So, in the PowerPoint I have, which is out, you know, it's in there. I hope you can see this better. I think you probably will be able to. But anyway, pons is a bridge of short cerebellum, this muscle movement, it's in the back of the brain. The midbrain clusters the sensory nerves. Thalamus is the switchboard that organizes things. Hypothalamus. This is all in that video, so watch that video. What I am going to talk about a little bit more, and he talks about this in that video. Oh, I have this. I can just as well use this. He talks about this in the video, is the cortex. The cortex is a specific strip and part of the brain. And as far as our sensory perceptions are concerned, and our movements are concerned, our voluntary movements are concerned, well, even some involuntary. But anyway, as far as our movements are concerned, this is the most critical and crucial part of the brain. Okay? So this is the motor cortex. The motor cortex is the parts that move, like when I do this. Whoa, my motor cortex is saying, do this. Whoa. And if I'm poking myself here, I don't know why I'm doing that, but I'm doing that when I feel it. The somatosensory cortex is actually the one that's firing up somewhere in that little section of my brain right now, so I can actually feel it. Those are really, really important. He talks about those in there as well, but I want to be a little more in depth with these. And you've seen these pictures briefly before, but I'm going to talk about them more now. You haven't seen this one. The motor cortex. You can take the motor cortex and put it over there. So this is the space dedicated on the motor cortex to the movement of these parts of our body. So on the motor cortex, we have very little movement of our trunk that we're able to do. Our hands, we have a ton of movement. Just think if you could move your thigh like you could move your hands. That'd be pretty creepy. You'd be like thigh hands. You grabbing stuff with your thigh. Super weird. But we can't. You can't move things around your body. But if you think of your face, you can do all kinds of crazy contortions with your face. Your mom's like, wait, your face is going to get stuck like that. And you actually wonder about it. Will it actually get stuck? No, it's not going to get stuck. So you have to tell your kids that too, whenever you have them. Anyway, so in our tongue, we can move our tongue a ton. I mean, I'm talking right now, I'm moving my tongue. It's going crazy moving around in there. But I can't do that with the other things on my body. I mean, I can move my toes. I can't do much with my foot. Just move it around a little like this. My leg, I can hardly do anything with. I mean, my actual torso, I can hardly do anything with. You know, you see. So it's so that's the idea. There's a massive amount of space devoted to that. Okay, and this is the somatosensory cortex. I put this one up for, by the power of Apollo, I command you to appear. Boom. Okay. So that's up there now, and so you see that one now. And I talked about this one before in another video. That's the somatosensory cortex. So this is how much of that part of the actual strip of brain is dedicated percentually to those things. And once again, that is what we would look like. That guy there, if our body was represented equally to the space devoted to these parts of the body on the somatosensory cortex, we would look like that dude. Big old face, because we have so many more sensations in our hands and so many more sensations in our face and our tongue than we have anywhere else in our body. You can just like test. You can like pinch different parts of your body, pinch your hand, pinch there, pinch the back of your leg. We have just sensed a lot more in these because these are so important parts for us, for our survival, I guess. But regardless of the reason, that's how it looks. Okay, so that's what those are. Now I'm going to talk about localization of function. This is important. Do not forget this, and don't forget the study. Don't forget the concepts that we're talking about. This is called localization of function. Now you see that link up there? That link will be in the description of the video. It is a University of Washington link, and it is excellent. It is actually written for kids. but it's actually the best simplistic explanation of the Sperry SplitBrain study that I've ever seen. It's really, really good. So look at that. I'm going to go over the Sperry SplitBrain study. Okay? And I'm going to try to do some cool graphic things with it up here to kind of illustrate. But I'll figure it out when I'm doing it. Anyway, okay? So take a look at that, read through it. It's only about a page and a half long or something. It's not much, but it's just well done. So anyway, okay, here's the premise. We have two halves of our brain. We have the left half of our brain, and we have the right half of our brain. Left half, right half. Okay. And so these two halves of the brain do different things. They have different functions. Now, there is something in between the two halves. Call it a router. Call it whatever you want. Actually, what you should call it is the Corpus Callosum, because that is what it's called, the Corpus Callosum. All right? So the Corpus Callosum connects the two brain halves, and it's a communication cable, basically. And it communicates and sends signals from one side of the brain to the other side of the brain. Anyway, so you've probably heard in lay terms, oh, you're such a left-brained person. Oh, you're so right-brained person. Okay? You might have heard that. And that is pretty much nonsensical. Yes, it is. That doesn't really have any sort of relevance in any real psychological sense. I mean, some people might like math more. It doesn't mean they're a left-brain person, that their left brain is more dominant or anything like that. That's what people try to say. But so, certain things are located in certain parts. Your brain does not do everything, as I've said before. Your brain, the left part of the brain, does things like this, as it says up here. Language, mathematics, logic, etc. Your language is over here, on the left part of your brain. Now, there's a crossover. So the left part of your brain controls the right side of your body, and the right part of your brain controls the left side of your body. My left eye is projected to the right hemisphere, and my right eye is projected to the left hemisphere. Okay? Now this doesn't make any difference, really, at all. At all. That's why I say this right brain, left brain is nonsense. This doesn't make any difference at all when there's a corpus callosum zipping back and forth, because all the stuff is communicated pretty much instantaneously. And yes, and so that's the case. So, okay, so your left hemisphere. So if I have a language problem, if I, for instance, were to have a stroke, or somebody like whacks me in the head with a baseball bat or whatever, and all of a sudden I can't talk, they know that there's damage where it is. We know exactly where it is. It's like in this area. It's kind of spread around, but it's like in certain particular areas. I mean, it's not that simple, but basically it kind of is. And so they would know where to look and to put me in a brain scan, put me in an MRI or something like that. But anyway, so it's on that. And also my math, and they know this from different things. They'll stick somebody in an MRI and they'll say, do a math problem, and you'll see where it lights up. They'll say, okay, I want you to do this logical problem, and it lights up over there. I want you to talk, it lights up over there. I want you to listen, it lights up over there, because speaking and understanding language are two different things altogether, okay? And so, how about the right hemisphere? What does the right hemisphere do? Well, the right hemisphere is better for spatial understanding and ability, okay? Facial recognition. So if you look at if they put you in an MRI, they're looking at your brain, the activity in your brain, they're actually looking at the brain, and they show you a picture of somebody, well, it's going to light up over here somewhere, right? Facial recognition, musicality, playing an instrument, it's going to be over here. Listening to music, it's going to be over here. Mental images, that kind of stuff. You think about a dragon, it would happen over there. And so generally, the lay term is somebody who's left-handed. That means their right hemisphere is dominant. This is not correct. But they're left-handed, the right hand, and you hear how lots of left-handed people are artistic, or a lot of artistic people are left-handed. Well, because it's supposed to be like your right brain is spatial understanding, musicality, that artistic type of stuff, whereas your left hemisphere is more math and logic and that kind of stuff. But that's not, there's a lot of left-handers that are artistic, and there's a lot of right-handers that are artistic. And I don't know if there's ever been an actual study done on artistic people, whatever that's supposed to mean, and handedness. An actual, real, legitimate study, because we probably wouldn't find any significant difference. But anyway, so those are the ideas there. And those things are located in those parts of the brain. That is not a debate, that is a fact, we know that. Those are located there, and they're located there, and we know where they're located, and we have a corpus callosum as a band of nerve fibers that transfers information back and forth pretty much instantaneously. So if you see something with your right eye, and it goes to your left side of your brain, that communicates to the right side of your brain, and it just works, okay? But what happens if you cut the corpus callosum? When you cut the corpus callosum, then you have something called a split brain, and you might be saying, why on earth would you want to cut the corpus callosum? Why would you go in and just cut the corpus callosum, open up your skull, cut the corpus callosum, close it back up, and say, get on with it? Why would you do that? Well, there's a reason, and they do it very rarely. The reason is basically when somebody has extremely severe epilepsy. I mean the kind of severe epilepsy that you fall down with seizures all the time. There's a lot of people that have epilepsy, and you can medicate a lot of it now. That's gotten a lot better. But there's some people that have, for instance, they'll have like hundreds of seizures, small little epileptic attacks in a day. And you divide that in hours, and how many minutes is that? There's a lot, and it's a lot, and so they lose concentration. But they want to do that for that type of person generally. What they would do if somebody was having really severe seizures where they fall down, they hurt themselves, and that whole kind of stuff, and you have to stop it. So epilepsy is an electric sort of disorder of the brain, to make it very simple. And if you think about, you can think about it like this. If you take a smooth pond and you throw a rock in it, okay, it puts ripples out. That's kind of like the idea. You have an epileptic attack and it puts ripples out, electrical ripples out. It's a metaphor. It isn't really correct, but it's kind of the idea. It puts electrical ripples out throughout the brain, and those electrical ripples, remember, our entire brain is electrical circuitry. And so, we do this and it just messes you up. But all of a sudden, let's say if you throw a boulder in there, kabloom, into not into your brain, but the pond, you see what I mean. And this is what a severe epileptic seizure is like. Now, what they found is that if they cut the corpus callosum, then it's not as easy for those epileptic seizures to be so big. It sort of stops that sort of, I guess it's feedback, and I'm not an expert by any means on epilepsy, so I just know that cutting the corpus callosum helps limit the severity of seizures. That's kind of the idea. And so they do that sometimes. So they do this procedure, they still do it. I think they do it less than they used to, but they still actually do the procedure. And it does help people, but it creates a kind of an interesting sort of like subject to be able to study, the split brain patient. And there are a number of them, and they've done a lot of split brain studies. And the guy, they was Sperry and Gonzaga. You'll see it in the names there. It's a hard one to remember. They won the Nobel Prize for this. This was a big thing, a big discovery. And so here's what happened. Here's what they found in the split brain studies. So what they did is they created something called a tachyon. And it's kind of like, you can kind of see it there. I'll put it there, obviously. You can kind of see it there. They're sitting in a thing, but they have kind of what they want to do is they want to have one visual projection on the right eye and one visual projection on the left eye, okay? So they kind of sit them in this thing. So you're kind of stuck and you're looking at one or the other. And then they flash an image of something to either eye, okay? So let's say that they take a ball, okay? And you flash the image of a ball to the right side. But remember, language is on the left side. So the image from the right side goes to the left side, and then you ask the person, what did you see? And the person says, I saw a ball. Okay? So what happens if you do it the other way? Let's say if you take another object, you don't want to have memory, so you take something new. Let's say you take a spoon, and you flash a spoon on the left side. Now there's nothing wrong with the eye. Flash a spoon on the left side. Okay? Got it? And it projects into the right side. And then you ask the person, what did you see? And the person says, I didn't see anything. What? I didn't see anything. Now, they saw it. Now, how do we know they saw it? What if you ask the person instead to use their right hand and pick out the object they just saw? And there's a bunch of objects in there. And what do? They pick out the spoon. And then you ask them, what are you holding? I don't know. They can't say it. I saw it. They identified it. The right side is not stupid. It knows exactly what it was, but it doesn't have the language capacity to deal with it. If that makes any sense. And it's very, very interesting. So this is sort of an idea of the split brain patient. There's also another one in their chimeric figures, which you'll take a look at, and I can talk a little bit more about it when we actually have our lesson, where there's a man on one side and a woman on the other side, and if you ask, anyway, so you'll see it. I'll just let you guys take a look at that one. So anyway, so here's how it looks here. That was my explanation there. Here's how it looks. What do you see? I see a ball. Okay? See the link? So what do you see on the other side? I see nothing. Showing on a hammer now. I see nothing. Whoops. And then the person can pick out the person can pick out the hammer, like I just said, or whatever it is. Okay. Okay. Anyway, all right. So now I'm going to talk about one other study here to talk about localization of function. 18 minutes. Let me check how. Yes, I will. I'm going to talk about this one. This is another one. And this is Brocas Area. You need to remember these two studies. These are critical studies to talk about localization of function, the ones that both of these. But I'll emphasize this more when we have our class, emphasize more about what localization of function is. But remember, localization of function is specifically that functions of stuff are located in specific parts of the brain. And so, okay, you have two different areas here. You have Brocas area and you have Brocas area. Now, this idea is not new that our brain is localized. There was something before called phrenology. That's what this chart is over there. The phrenology, and phrenology was just the idea. This sounds really stupid. That the bumps on your head talk about are specific to your personality. I could talk a lot more about it than I do in TLK, but it's just silly. It's a science that doesn't work anymore. But the idea has been there for a long time that different areas of our head, our brain, or our head at least, do different things. Anyway, so Broca was a doctor, and he's the first one to discover really that there was a speech area. So 1860s in France, it arises out of the concept of phrenology, which I just talked about, based originally on case studies of two patients. Okay? There was somebody who had a stroke, and his name was Lebourg, I guess. And he could only say one word after his stroke. He was fine before that, and after his stroke, he could only say one word. Tan, 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 tan. Hodor, 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 hodor. So if you watched Game of Thrones, you know what I'm talking about. And now you know what was wrong with Hodor, because he can only say Hodor. He had damage to his Brocas area. Anyway, there was also Lelong, who suffered also stroke, and he could say oui, non, toi, toujours, and his name Lilo, which was misspoken. Okay, that's all he could say. And so they died not long after, and Broca decided he would cut their heads open and take a look at their brain and see what was going on. What was going on with their brains? And so this is actually the first one, Lebourg, that's his brain, an actual real brain. And the front of the brain, I'm going to put those images up over here, put that image up over here first. On the front of the brain, that's the brain that way is where the eyes would be on the skull. So that's the front of the brain. Back there is the cerebellum, which is for motion and things like that. But anyway, so on the front of the brain, you see there's a huge, it's right there, probably, I'm not exactly sure where it's going to be there, but that you see that crater for the front left-hand side of the brain. That is called Brocas Area now. And that is the part of area that is responsible for speech. So what happened is he had a stroke, okay? The brain cells in that area died, and once brain cells die, your body kind of sucks them back to all the material back together, and it just kind of disappears, the brain. So he's got a crater in there. And if you look at that, it's like completely all messed up. And you see the other image, I'll put that one up over there. Oh. Those are the areas which are problematic, and those are the speech areas of the brain. And so he discovers this. Now I'm gonna link that one. Actually, you can just link that one through. You can just look at that one through the actual PowerPoint. But that's a very interesting study because scientists revisited this study. They revisited Broca. That's the second ones were from that. The second videos or slides were from that. The pictures, whatever it was, the second ones that I showed you were from the new study. And they didn't actually slice the brain up, but they looked at micro slices of the brain through through image technology. And what they found is that actually the damage in his brain was all over the place, that there was a lot of it. And it says why his speech was so damaged. He can only say one word. Likely there's other parts of the brain which are speech areas of the brain too. And it makes sense that speech is so important for humans. But absolutely, Brocas area is a part of the brain that is located for speech. Okay. And so here's, I'll continue on this one. This is good. I wanted to do 2 proper lessons to get us moving into this anyway. So the brain continued language, Brocas area, that's in this area here that you're showing. You'll see it. I'll put it up there. And then there's also Wernicke's area. Wernicke's area is for receiving speech, for comprehending speech. And this is interesting. They're different areas altogether. One thing, if I talk to you and you understand, it's firing up in a different part of the brain, and that is called Wernicke's area. And there are examples. There's some YouTube videos that I have on the next slide that are really, really quite interesting, where people understand what is being said to them, but they can't reproduce it. And you can also see times when they can produce language, but they can't understand it. And you can't really talk back to somebody if you don't understand what's being said. But they don't have a problem producing language. They just don't. It's nonsensical because they can't comprehend what's going on. And so this is the idea behind these things. And so there's a bunch of videos there, and there's quite a few videos for you guys to watch this time. But watch these videos. I will link all of them into the description here, so you can just easily click on them. Although you can get them out of the PowerPoint as well. But these Sarah Scott videos are really interesting. Sarah Scott was I think she was 18 or 19 when she had a stroke. Well, not very many young people get them, but they do. And she got Brocas aphasia. And I think the second one is 7 years on or something like that, or was it 6 years on? She makes a new one every year to kind of catalog her progress. So if you just look up Sarah Scott, look at the first one I have linked there, and then look at if she continues. She continues to get better and better, and it's kind of interesting to see as she gets older and older. But still, she's still damaged. Her language production is still damaged, and it really, handicapped her for life in a lot of ways. But it's interesting to watch. Pretty good videos, interesting stuff. But you've got to watch the videos that I put out here. Not only my video, obviously, but you've got to watch these videos. It's like really, really important because it's an important example for you guys to use. And so with that. Oh, my goodness, these battles have caused me to tire. So what I need to do now is I need to go have a seat. Please, musicians, thank you, I deserve all the attention I can get. I've saved this country from certain demise because I am so fierce and brave. Now, I shall go sit in my gilded chair, and I shall await the servants to bring me meat and bring me drink. That's right. May Zeus be with you.